At this very moment, you might be trapped inside the most massive prison imaginable. Not a cell with bars or a planet ruled by gravity, but a black hole. Evidence from the James Webb Space Telescope shows galaxies spinning in ways that defy expectations. Calculations reveal that the size of our universe aligns almost exactly with the dimensions of a collapsed star. From researchers in Barcelona to theorists in Princeton, the math checks out. The Big Bang may have been a rebound inside something far larger than we can comprehend. If you love exploring cosmic mysteries, hit subscribe, because what comes next could transform your view of reality. Get ready, we begin. Imagine a sphere containing everything you can observe, every star, every galaxy, every particle of light that has reached Earth over nearly 14 billion years. Now compress all that mass into a single point and calculate the size of the black hole it would create. The answer is shockingly precise. The radius matches perfectly. In 1916, Carl Schwarzschild solved Einstein's equations and discovered something disturbing. Any mass compressed within a specific radius becomes a black hole. The size of that radius depends only on mass. More mass means a larger radius. This relationship follows one rule: double the mass, double the radius. Physics experiments have confirmed this principle countless times. Scientists have measured the observable universe, its mass, and its radius. When they plug those values into Schwarzschild's equation, an unexpected result appears. The universe's actual radius equals the radius at which all its mass would form a black hole's event horizon. This isn't a coincidence. The numbers line up with incredible precision. Most physicists dismiss this as an oddity, arguing that the universe expands differently from the way black holes collapse. They point out there is no outside for our universe to be inside a black hole. While these arguments sound logical, math doesn't care about logic. It only cares about truth. In 1972, theoretical physicist Raj Pathria published a paper in Nature suggesting that our universe might be confined within a black hole's boundary, even while appearing to expand from the inside. His work was largely ignored at the time, since black holes were still poorly understood, but the calculation held. Decades later, new observations revealed that our universe sits precisely at the threshold of becoming a black hole. The implication is deeply unsettling. Black holes scale with mass in peculiar ways. Small black holes are extremely dense, compressing several stellar masses into tiny spaces. Supermassive black holes, by contrast, stretch their mass across enormous distances. A black hole containing the mass of our universe would have an average density similar to what we observe around us, just a few hydrogen atoms per cubic meter. From the inside, you wouldn't notice anything unusual. Some physicists, such as Shah Carroll, argue this doesn't mean much, claiming that universes with zero curvature naturally follow this relationship. But others think the pattern is too precise to ignore. Why does our universe sit exactly at this threshold? Why does it expand at the precise escape velocity from itself? These questions only deepen as we learn more. What astronomers discovered in 2025 adds another layer of complexity. Einstein's equations allowed for a rotating universe, not galaxies rotating within space, but space itself spinning like a cosmic carousel. This wasn't mere speculation. Gödel's solution satisfied every requirement of general relativity. In his rotating universe, you could travel in a large enough circle and return to your own past without wormholes or exotic matter, just by moving along a specific path through ordinary space. The math allowed for closed time-like curves, loops in spacetime where cause and effect circle each other endlessly. You could literally shake hands with your past self before departing. Einstein hated this outcome. He admitted the solution was mathematically valid, but insisted that backward time travel must be physically impossible. Yet Gödel's findings showed otherwise. General relativity, Einstein's own framework for describing space and time, allowed time loops without hesitation. This created a profound problem. If general relativity permits time travel, then either the theory is incomplete, or time itself behaves differently from what we assume. Gödel believed he had exposed a fundamental flaw. Time may not exist at all, but instead be an illusion experienced by observers moving through a fixed four-dimensional geometry. Scientists searched for signs of cosmic rotation by analyzing distant galaxies and studying the cosmic microwave background. They found nothing. If the universe rotates, it does so by less than 1/110 quadrillionth of a degree per century. But the James Webb Space Telescope changed everything in 2021. Its extraordinary resolution captured galaxies from the early universe, revealing something unexpected. 2/3 of the 263 galaxies observed rotated in the same direction as the Milky Way, while only 1/3 rotated the opposite way. This symmetry shouldn't occur randomly. The chances of such a distribution happening by accident are nearly zero. Either our methods of measuring galaxy rotation are flawed, or the universe has a preferred direction. Something deeper is influencing it. In early 2025, Lior Shamir published his analysis in monthly notices of the Royal Astronomical Society. He offered two possibilities. Either the universe was born rotating exactly as Gödel's equations predicted, or our measurements are distorted by Earth's own motion through space in ways we haven't yet accounted for. Both possibilities suggest something troubling. Our understanding of the universe may be incomplete, and it's possible we are inside a black hole. Every black hole has an event horizon, an invisible boundary marking the point of no return. Beyond it, escape becomes impossible. Light cannot get out, information cannot leave, and the interior becomes sealed off from the rest of reality. We've imaged event horizons around supermassive black holes, like the glowing ring of matter circling the darkness at the center of our galaxy. This darkness is not empty. It is a region from which no light can escape. Now consider our universe. We have our own horizon, the cosmological horizon. Light moves at a fixed speed, and the universe has a finite age, so light from extremely distant regions hasn't had time to reach us. There's a sphere around Earth beyond which we cannot see. This forms a natural boundary. We can observe light up to about 46 billion light years away, even though the universe is only 13.8 billion years old. Expansion has stretched incoming light, but a limit remains. Beyond our cosmological horizon, events occur that can never affect us. Information from beyond that boundary will never reach our telescopes. These two boundaries share striking similarities. A black hole's event horizon traps light inside, while the universe's expansion prevents light from reaching us. Physicist Leonard Susskind argues that these boundaries might actually be the same phenomenon viewed from different perspectives. The cosmological horizon could be the event horizon of the black hole we inhabit. The expansion of space might simply be the interior geometry of that black hole. This idea, known as the holographic principle, proposes that all the information about space is encoded on its boundary. A universe inside a black hole would contain only as much information as could fit on its event horizon. In the 1970s, Gerard Hooft advanced this theory, showing that black hole entropy depends on surface area, not volume. A black hole twice as large has 4 times the entropy. This suggests a deeper link between black holes and the universe. If our universe exists inside a black hole, everything we perceive might be a projection from a distant 2-dimensional surface. Depth and 3 dimensions could be illusions. This remains theoretical, but it offers a way to understand why both the event horizon and the cosmological horizon behave similarly. Each creates a region causally disconnected from its surroundings, one trapping light inside, the other blocking light from entering. The singularity problem remains unsolved. At the center of every black hole, general relativity predicts a singularity, a point of infinite density. But the mathematics of gravitational collapse breaks down there. This is a major issue. The theory stops making sense. Some researchers believe quantum mechanics might prevent true infinities, but without a quantum theory of gravity, the problem persists. What makes this even more troubling is that the singularity at the Big Bang and the singularity inside a black hole share the same mathematical form. They aren't just similar, they may be identical. In 1972, Raj Pathria suggested that the Big Bang singularity could actually be the singularity inside a black hole. If this is true, our universe would be the interior of a black hole formed from the collapse of a larger parent universe. From the outside, it would appear as an ordinary collapsed star, but inside, space-time would expand, temperatures would fall, and an entire universe would emerge from what seems like a point. This could offer an unexpected solution to the singularity problem, implying that what appears to be infinite density is simply a moment of maximum compression before the universe rebounds. Density reaches an extreme yet finite value before reversing its collapse. Polish physicist Nikodem Pawlowski carefully mapped the process. His calculations demonstrated that including torsion, a geometric property usually ignored in general relativity, allows the bounce to occur naturally. At extremely high densities, the interplay of quantum mechanics and rotating matter produces repulsive forces that halt collapse. The universe rebounds. What emerges appears identical to our cosmos, with matching expansion rates, thermal history, and structural formation. Observers inside cannot tell if they reside in a conventional Big Bang universe or a black hole that bounced. The mathematics are consistent, the physics checks out, and the theory provides testable predictions. Yet it challenges intuition. Perhaps we do not inhabit the universe itself, but something far more intricate. Chapter 5. A universe born spinning the James Webb Space Telescope, a $10 billion endeavor spanning 3 decades, launched in December 2021, positioning itself nearly 1 million miles from Earth. Its 21-foot mirror captures infrared light from the universe's earliest galaxies. Early observations revealed unexpected insights, notably from Lior Shamir, who studies galactic shapes and rotations. Shamir analyzed 263 galaxies, noting clockwise versus counterclockwise rotation. In a perfectly isotropic universe, one would expect a 50-50 split. Instead, roughly 2/3 spun clockwise, 1/3 counterclockwise. Published in monthly notices of the Royal Astronomical Society in February 2025, these findings suggest space-time itself could rotate. Galaxies might inherit their spin from the universe's geometry, consistent with black hole cosmology. A universe forming inside a rotating black hole inherits angular momentum from the parent collapse. However, decades of observations present challenges. Cosmic microwave background measurements and quasar studies show no evidence of universal rotation. The universe may rotate extremely slowly, or our measurements of distance and motion may introduce systematic bias. The Milky Way's rotation affects apparent brightness and color of galaxies via Doppler effects, creating observational asymmetries. Recalibrating these measurements may require adjusting the cosmic distance ladder, potentially resolving inconsistencies in expansion rate determinations. Rotation patterns and cosmic history galaxies farther away exhibit greater asymmetry, implying that the universe's rotation was stronger in the past and has slowed over time. This aligns with the hypothesis that space-time inherited angular momentum from a collapsing black hole. Chapter 6. The Scientist Who Charted the Impossible. Nikodem Pawlowski, physicist at the University of New Haven, investigates Einstein-Cartan theory, an extension of general relativity introducing torsion, the twist of space-time caused by particle spin. Standard relativity treats gravity as curvature of space-time from mass and energy, ignoring intrinsic spin. At extreme densities, spin becomes crucial. Pawlowski showed that torsion generates a repulsive force at high density, counteracting gravity and preventing singularities. Fermions, the particles forming matter, cannot occupy identical quantum states due to the Pauli exclusion principle, producing repulsion arising purely from space-time geometry. While negligible at ordinary densities, torsion becomes significant at nuclear scale densities, acting like a spring to halt collapse and trigger the big bounce. This framework naturally explains cosmic inflation, galaxy rotation patterns, and the universe's structure without invoking exotic matter or violating known physics. It also supports the possibility that our universe exists within a black hole, reshaping fundamental cosmology under the DocuVerse perspective. DocuVerse Insight, the Big Bounce and Spinning Universe. At a specific point, the universe reaches an extreme yet finite density and begins to reverse its collapse. This phenomenon, known as the Big Bounce, was meticulously worked out by Polish physicist Nikodem Pawlowski. His calculations revealed that by including torsion, a geometric property often neglected in general relativity, the universe's bounce happens naturally. Quantum mechanics, combined with rotating matter at these extreme densities, creates repulsive forces that halt the gravitational collapse. The universe then rebounds outward. The result is indistinguishable from our own universe. It shares the same expansion rate, temperature history, and structural formation. From inside, one cannot tell whether they are living in a conventional Big Bang cosmos or inside a black hole that has undergone a bounce. The math checks out, the physics are sound, and the theory offers predictions we can potentially test. However, this theory requires us to accept a radical concept that we are not living in the universe itself. Instead, we could be living inside something far more complex. DocuVerse Insight, a universe born spinning. The James Webb Space Telescope, an engineering marvel that cost $10 billion and took 30 years to complete, was launched in December 2021. Positioned nearly 1 million miles from Earth, it boasts a 21-foot mirror capable of detecting infrared light from the earliest galaxies. When the telescope began transmitting data, astronomers were prepared for surprises, but not the ones they received. One such discovery came from Lior Shamir, an astronomer specializing in galaxy shapes. Shamir studied the rotation of spiral galaxies and found that 2/3 of the 263 galaxies he analyzed rotated clockwise, while only 1/3 rotated counterclockwise. This finding directly contradicts the assumption that galaxy rotation should be random in an isotropic universe. If the universe were truly isotropic, we would expect a 50-50 split of clockwise and counterclockwise rotations. Instead, Shamir's findings suggest that the universe might not be isotropic after all. His results, published in monthly notices of the Royal Astronomical Society in February 2025, point to a possible deeper reality. Space-time itself may be rotating. This idea, first proposed 76 years ago, suggests that space itself could rotate, carrying galaxies along with it. If this is true, the galaxy's rotation might be inherited from the geometry of the universe, leading to a preferred direction. While the idea aligns with black hole cosmology, where the universe could have formed inside a rotating black hole, current measurements, like those of the cosmic microwave background, show no clear evidence of universal spin. However, Shamir's data suggests that the universe's rotation may be too slow to detect with current technology. Alternatively, this discrepancy might be due to flaws in our measurements of cosmic distances, which could be influenced by the motion of the Milky Way through space. This could mean that recalibrating our methods could resolve many of the long-standing issues in cosmology. The scientist who mapped the impossible, Nikodem Pawlowski, a physicist at the University of New Haven, Connecticut, is the mind behind the Big Bounce theory. Pawlowski's work began with studying Einstein-Cartan theory, an extension of general relativity. General relativity explains gravity as the curvature of spacetime caused by mass and energy. Einstein-Cartan theory, however, adds torsion, a twisting of spacetime caused by the spin of matter. While standard relativity works well under normal conditions, it fails to account for the effects of particle spin at extremely high densities. Pawlowski realized that at these high densities, such as near black holes or at the Big Bang, spin becomes crucial. He discovered that torsion can create a repulsive force that opposes gravitational collapse. This force is what allows the universe to bounce rather than collapse into a singularity. The Big Bounce, a new understanding of the universe's origins. In the traditional Big Bang model, the universe begins from a singularity, a point of infinite density. However, in Pawlowski's model, the Big Bang is not the beginning of the universe, but the reversal of a collapse. Instead of the universe collapsing into infinite density, matter reaches a maximum density, roughly 100 million times the density of atomic nuclei, and then rebounds outward. The collapse is halted by the repulsive force from torsion, and the universe expands. This bounce is what we observe as the Big Bang. From an external perspective, the formation of a black hole looks completely normal. The event horizon appears, and matter seemingly disappears inside. However, inside the event horizon, time and space exchange roles. What we observe as the future becomes a spatial direction within the black hole. The Big Bang moment, which was traditionally considered a singularity, becomes a moment in time, not a point of infinite density. Pawlowski's calculations, which were published in high-profile journals like Physics Letters B and General Relativity and Gravitation, confirm that this bounce is a natural outcome of Einstein-Cartan gravity, with no need for exotic matter or violations of known physics. Yet, despite its logical and mathematical rigor, many scientists initially dismissed the theory because it was so radical, too strange, too different from conventional thinking. What torsion does to spacetime. In Einstein-Cartan theory, torsion represents the twisting of spacetime caused by the spin of particles. While this effect is negligible at normal densities, it becomes crucial at extreme densities, such as near black holes or during the Big Bang. When matter compresses, the repulsive force created by torsion grows rapidly, eventually overpowering the pull of gravity. This halts the collapse and causes the universe to rebound. Torsion provides a natural explanation for cosmic inflation, the rapid expansion of the universe after the Big Bang. In the standard cosmological model, inflation is driven by a hypothetical field called the inflaton. However, in the Big Bounce model, inflation occurs automatically as a result of the repulsive force from torsion. The mathematics of the bounce predict both inflation and dark energy without the need for new components or fields. A universe within a black hole. One of the most exciting implications of Pawlowski's theory is the idea that our universe might exist inside a black hole. If the universe formed inside a rotating black hole, each black hole would give birth to new baby universes inside it. These universes would be nested like Russian dolls, each inheriting slightly modified physical laws from their parent black hole. This theory suggests that the universe is not a singular entity, but part of an eternal cycle of collapse and rebirth. Each cycle could create new universes, which would, in turn, give rise to more universes. This process could explain why the universe exists at all, not as a creation from nothing, but as part of an ongoing cycle of collapse and expansion. In 2010, Pawlowski's theory was published, and although it was not immediately confirmed, it captured the imagination of many scientists. It was listed among the top theoretical discoveries of the year by National Geographic and Science magazine. The idea that black holes could give birth to new universes challenges the conventional understanding cosmology and provides new insights into the nature of existence. After 380,000 years, electrons combine with nuclei to form atoms. The universe becomes transparent to light. Photons decouple and stream freely through space. These photons, stretched by 13.8 billion years of expansion, reach our telescopes as the cosmic microwave background. Temperature dropped from 3000 Kelvin to 3 Kelvin. Wavelength stretched from visible light to microwaves. Once again, observations match theory precisely. The microwave background has the exact temperature and spectrum predicted. Its small variations in temperature across the sky match the density fluctuations expected from quantum fluctuations during the bounce. No modifications needed, no fine-tuning required. The bounce scenario explains everything, standard cosmology explains, but it adds something crucial. It removes the singularity. The moment where physics breaks down simply does not exist. Density reaches a maximum, time continues, and equations remain valid. No infinities appear, no breakdown occurs. This bounce did not happen in our universe. It happened in a black hole that formed in another universe. What we call the Big Bang was the moment of maximum compression inside that black hole's event horizon. The expansion we observe is the interior geometry of spacetime beyond the horizon. From outside, observers in the parent universe saw a star collapse normally. Mass exceeded the critical threshold. Spacetime warped beyond recovery. An event horizon formed. Light stopped escaping. The black hole settled into a stable state. Nothing unusual happened. But inside, beyond the point where information cannot escape, a universe exploded into existence. Time and space exchanged roles. The singularity at the center became a moment in time rather than a place in space. That moment was the bounce. The transition from maximum compression to rapid expansion. Our entire cosmos, with its hundreds of billions of galaxies, each containing hundreds of billions of stars, exists in a region that appears from outside to be a single point at the center of a black hole. The vast scale of space and time we experience is an illusion created by the geometry beyond the event horizon. And if this is true, then every black hole we observe creates universes just like ours. The cycle never ends. Collapse, bounce, expand, create black holes. Those black holes bounce and create more universes. Those universes create more black holes. An eternal tree of nested realities, each generation inheriting physics from its parent. But how do we test this? How do we confirm or rule out living inside a black hole? The answers come from understanding what unique predictions the bounce theory makes. Inside another universe's black hole, the black hole that contains our universe formed long ago, not in our time, but in the parent universe's time. A massive star exhausted its fuel and collapsed, or perhaps a dense region of space underwent gravitational instability. The exact mechanism doesn't matter, only the outcome. An event horizon formed. Mass compressed within its Schwarzschild radius. Space-time was warped so severely that escape became impossible. From the parent universe's perspective, this took finite time, perhaps seconds for a stellar black hole, perhaps millions of years for a supermassive collapse. But it finished. The horizon stabilized. The black hole achieved equilibrium. Inside, time behaves differently. What appears as the center of the black hole from outside corresponds to a moment in time from inside. That moment is our Big Bang, the instant when density peaked and began decreasing, when expansion started, when our cosmic clock began ticking. This creates a bizarre relationship between parent and child universes. The entire history of our universe, from the Big Bang to heat death trillions of years in our future, exists simultaneously from the parent universe's viewpoint. Our time is a coordinate direction inside their spatial geometry. They see the event horizon as a surface in space. We experience it as an infinite future we can never reach. Enrique Gastiaga from the Institute of Space Sciences in Barcelona calculated the details in 2025. His team's paper in Physical Review D worked out the exact geometry. They showed that the black hole's mass must equal the total mass of our observable universe, about 3 × 10⁻⁴ kilograms. Compressed to a Schwarzschild radius of approximately 13.7 billion light-years, these numbers match. The observable universe has roughly this mass. It extends roughly this distance. The black hole containing our cosmos would have these exact properties. The fit is not approximate, it is precise within measurement uncertainty. From outside, this black hole appears unremarkable. Its mass equals roughly 5 × 10⁻² stellar masses, enormous by stellar standards, but small compared to supermassive black holes at galaxy centers, which reach billions of stellar masses. The black hole containing our universe would be unusually large, but not impossible. It might not even be the only one. If black holes create universes, and universes create black holes, then the parent universe likely contains many such objects, each one harboring an entire cosmos, each completely isolated from the others and from the parent, separate realities existing within space-time pockets, unable to communicate or interact. This solves a long-standing mystery. Where did our universe come from? Standard cosmology offers no answer. The Big Bang simply happened. No cause, no explanation, just an initial condition imposed by hand. The equations start with everything already expanding from infinite density. Why? No reason given. The theory is silent about origins. Black hole cosmology provides an answer. Our universe came from gravitational collapse in another universe. That parent universe might have come from another collapse before it, an infinite chain stretching backward with no beginning. Or perhaps a cycle where universes eventually collapse and bounce again, creating themselves in an eternal loop. Either way, no creation moment exists. No first cause required, just physics operating according to known laws. Can we ever know for certain? But this raises uncomfortable questions. If we are inside a black hole, can we ever know for certain? Can we observe evidence of the parent universe? Or are we trapped behind an informational barrier that prevents any signal from reaching us? The event horizon works both ways. It prevents information from leaving our universe, but also prevents information about the exterior from reaching us. We cannot see what lies beyond our cosmological horizon. We cannot detect the parent universe. The boundary is absolute, yet the theory makes predictions. Each rebound spawns expanding spacetime, universes within universes, nested endlessly. This means black holes are not destroyers, they are creators. Every stellar mass black hole gives birth to a universe containing trillions of galaxies. Every supermassive black hole at a galaxy's center creates a cosmos far larger than ours. The bigger the black hole, the larger the universe inside. Mass scales directly with volume. From inside, each universe appears infinite or nearly so. Expansion continues indefinitely. Time stretches toward eternity. But from outside, the entire structure is finite, bounded by the event horizon. Existing in a localized region of the parent spacetime, we might be asking the wrong question. Instead of wondering whether we live in a black hole, we should wonder how many black holes contain universes like ours. The answer, if this theory is correct, is all of them. Every single one. This transforms cosmology completely. The universe is not unique, not special. One cosmos among countless others. Each isolated, each experiencing its own expansion, its own evolution, its own structure formation, all connected through the physics of gravitational collapse, but unable to communicate or interact. And if every black hole creates universes, and those universes create more black holes, then the multiverse is not speculation. It is inevitable, a tree of realities branching endlessly. Quantum mechanics and the exclusion principle. Our cosmos is one leaf among infinite branches, one bubble in an infinite foam, one note in an eternal symphony of expanding spacetimes. But the most testable prediction comes from understanding how quantum mechanics prevents the singularity. The mechanism that makes the bounce possible, the rule that saves spacetime from catastrophic failure, is the Pauli exclusion principle. Discovered by Wolfgang Pauli in 1925, this principle seemed to be a minor detail about electron orbits in atoms. No two electrons can occupy the same quantum state. Each must differ in at least one quantum number, spin, energy level, or angular momentum. This rule explains why atoms have structure, why electrons fill specific orbitals, and why the periodic table works. Without the exclusion principle, all electrons would collapse into the lowest energy state. Atoms would be featureless, chemistry wouldn't exist, and neither would life. But the Pauli exclusion principle applies to all fermions, not just electrons, protons, neutrons, quarks, neutrinos. Every particle with half-integer spin cannot share quantum states. This principle, though abstract, has profound consequences when it comes to high-density matter. As matter compresses, particles move closer together. Eventually, they run out of available quantum states. The lowest energy levels fill completely. New particles must occupy higher energy states. This creates pressure even at zero temperature, degeneracy pressure, not from heat, but from quantum mechanics forbidding further compression. White dwarf stars, for example, are supported by electron degeneracy pressure. Their cores compress until electrons cannot get closer without violating the exclusion principle. The star stabilizes at densities around 1 billion kilograms per cubic meter, and this is confirmed in observations of thousands of white dwarfs. Similarly, neutron stars stabilize through neutron degeneracy pressure at nuclear densities. But what happens when gravity exceeds neutron degeneracy pressure? Standard physics suggests nothing can stop the collapse. The star becomes a black hole and the singularity forms. But Einstein-Cartan theory offers an alternative. The exclusion principle operates through torsion at these extremes. Fermions couple to spacetime twist. The coupling grows stronger as density increases, and eventually, torsion pressure exceeds gravitational compression. The collapse halts. Calculations by Enrique Gastiaga in 2025 confirmed this precisely. His team showed that when matter reaches approximately 10^360 kilograms per cubic meter, torsion repulsion completely stops collapse. Density cannot increase further. This is the breakthrough that prevents singularities from forming. The Big Bounce and the mystery of dark energy. The two theories naturally combine, creating a framework that inherently prevents singularities. This fusion makes testable predictions, one of the most significant being that our universe should have small but detectable spatial curvature. It's not perfectly flat, more like the slight curvature of Earth's surface. This curvature results from the initial conditions of the collapse. The overdense region that formed the black hole wasn't a perfect sphere. It had slight asymmetries, which translate into curvature after the bounce. Current measurements suggest the universe is flat within about 1%, but with advancements in instrumentation, this figure could be refined. The European Space Agency's Euclid satellite, launched in 2023, is set to measure curvature with 10 times more precision. If the bounce theory holds, Euclid should detect a positive curvature of about 2%, a small but definite deviation from flatness. This is a falsifiable prediction. If Euclid finds perfect flatness or negative curvature, the bounce theory would fail, proving the model wrong. This is how science works: make precise predictions, build instruments to test them, and accept the results. Another significant prediction from the bounce theory involves the cosmological constant, commonly associated with dark energy. Standard cosmology treats dark energy as a mysterious component filling space with energy that remains constant over time, requiring impossible fine-tuning. Why does dark energy have exactly the value needed to accelerate expansion without tearing space-time apart? Bounce cosmology offers a natural explanation. The cosmological constant arises from residual torsion left over from the bounce. As space-time expanded, most torsion dissipated, but a small amount remains, generating negative pressure that accelerates the expansion of the universe. This value is not arbitrary, it's determined by the bounce dynamics. The theory calculates it directly from fundamental principles. Gastiaga's team computed the expected cosmological constant, and their results align with observational data within uncertainty. No fine-tuning is required, no need for anthropic reasoning, just the logical consequence of bouncing from maximum density. The theory also predicts specific features in the cosmic microwave background, CMB. Quantum fluctuations during the bounce should create temperature variations with particular statistical patterns. These patterns differ subtly from those predicted by standard inflation theory. Future measurements might detect these differences. But the most profound implication of the bounce theory is its philosophical impact. If the exclusion principle prevents singularities, physics never truly breaks down. General relativity remains valid everywhere, no quantum gravity needed, no new theories required. The universe is completely understandable using the laws of physics we already know. Singularities were simply mathematical artifacts, ghosts created by incomplete equations. Once you include all relevant physics, they disappear. Reality is continuous. Time flows forward, density reaches extreme values, but never infinity. The equations always work, suggesting something deep about nature. The laws of physics are complete. They are sufficient to describe reality at all scales, from atoms to entire universes, across every energy level. The same principles operate universally, and these principles suggest, undeniably, that we live inside a black hole. Not maybe, not possibly, but inevitably. The mathematics demand it. The collapse and expansion cycle. Enrique Gastiaga spent years working on a critical problem. Not whether black holes create universes, but what happens during gravitational collapse when quantum mechanics becomes significant. His team at the Institute of Space Sciences in Barcelona approached the issue mathematically. They began with a cloud of matter undergoing gravitational collapse, assuming it to be spherically symmetric and uniform. These standard assumptions simplified the equations while retaining the core physics. Then they incorporated Einstein's field equations modified to include quantum pressure derived from the Pauli exclusion principle. The team worked through hundreds of pages of calculations, solving the equations analytically where possible and numerically where necessary. They double-checked their work, verified boundary conditions, and ensured energy and momentum were conserved, standard procedure in theoretical physics. What emerged was a complete solution, a mathematical description of collapse, bounce, and expansion that satisfied all the conditions. No approximations, no hand-waving, just exact results derived from fundamental principles. Their paper, Gravitational Bounce from the Quantum Exclusion Principle, appeared in Physical Review D in May 2025. The title understated the implications. They had solved the origin of the universe. The solution showed that collapse cannot proceed to a singularity. As density increases, quantum pressure grows faster than gravitational attraction. There is a turning point, maximum density, where the collapse halts and reverses. This turning point is not artificially inserted, it emerges naturally from the equations. At maximum compression, the universe reaches finite size. Gastiaga's calculations give a radius of about 1 Planck length, 10^35 meters. Incredibly small, but not zero, not infinitely small. It's an actual finite size with a definite geometry. At this moment, density reaches approximately 10^96 kilograms per cubic meter, and temperature exceeds 1032 Kelvin. These values are extreme, but they're not infinite. The equations remain valid. Physics continues to work. The next step? Expansion. The quantum pressure that halted the collapse continues to push outward. Space-time stretches, volume increases, density and temperature decrease. Solving inflation's fine-tuning problem. This bounce does not happen instantaneously. It takes time, very little time by human standards, but finite time nonetheless. The first few microseconds after maximum compression, the universe expands exponentially. Volume doubles every 1044 seconds. This is cosmic inflation, not driven by some hypothetical inflaton field, but by the dynamics of the bounce itself. The same force that halted collapse drives rapid expansion. Inflation ends when quantum pressure drops below a critical threshold, but expansion continues at a slower rate. The universe transitions to radiation-dominated expansion, and standard Big Bang cosmology takes over. This solves inflation's fine-tuning problem. In standard inflationary models, the inflaton field needs to start with exactly the right energy density. Too high, and inflation never ends. Too low, and it never starts. The window is absurdly narrow, 1 part in 10 to 120, which is difficult to explain without invoking luck or multiple universes. Bounce cosmology has no such problem. The initial conditions are set by the collapse. Any collapsing cloud of sufficient mass produces the same bounce, the same inflation, and the same evolution. No fine-tuning required, just physics. The source of dark energy. The theory also explains dark energy. After inflation ends, some quantum pressure remains. Not much, just a tiny fraction of the peak value, but enough to create negative pressure in the vacuum. This residual pressure causes the accelerated expansion we observe today. Gastonaga's calculation predicts the dark energy density to be around 410-10-10-10 joules per cubic meter. Observations show approximately 610-10-10-10 joules per cubic meter. The match isn't perfect, but it's remarkably close, given the uncertainties in both theory and observation. No other theory of dark energy predicts its value from first principles. Spatial curvature and the future of bounce cosmology. The bounce theory also makes a striking prediction. The universe must have positive spatial curvature. It's slight, but detectable. This curvature emerges because the collapsing cloud wasn't perfectly uniform. It had small density variations. After the bounce, those variations manifest as curvature in the expanding universe. The predicted curvature is small, about a 2% deviation from flatness. Current observations can't rule this out. They constrain curvature to within 1%. Future observations, particularly from Euclid and other missions, will have the sensitivity to test this prediction. If positive curvature is detected near the predicted value, the theory will gain strong support. If perfect flatness or negative curvature is observed, the theory fails. The ultimate revelation. This is the core of genuine science: testable predictions, falsifiable claims, observable consequences. The most profound contribution of Gastonaga's work is showing that the bounce occurs within the framework of standard physics. No exotic matter, no modified gravity, no extra dimensions. Just Einstein's geometry plus quantum mechanics. The two theories combine naturally, and their combination forbids singularities and produces bounces. This means every black hole bounces. Not just the one that created our universe, but every single black hole, every stellar mass black hole, every supermassive black hole, all of them. Each one creates a universe inside its event horizon. The origin of dark energy and the bounce theory. As the universe expands, matter density decreases, and eventually the negative pressure from residual torsion outweighs the positive density from matter. This shift accelerates the expansion. This transition took place around 5 billion years ago, with matter density dominating prior to that point. Gravity slowed down the expansion, leading to the formation of galaxy clusters and the growth of structure via gravitational collapse. However, when dark energy took over, the expansion accelerated, halting further growth of the largest cosmic structures. Recent observations confirm this timeline. We can observe fewer massive galaxy clusters forming in the present compared to the past. The large-scale structure of the universe effectively froze about 5 billion years ago. While new galaxies still form and stars continue to ignite, the largest structures spanning hundreds of millions of light years stopped growing as dark energy became dominant. Gastonaga's calculations predict the exact timing of this transition based on bounce parameters, and the results align with observed data within the expected margin of error. This theory is grounded in measurable physics with no adjustable parameters, only fundamental principles. A significant implication of this theory is its prediction of the dark energy density. The residual torsion pressure, which depends on the amount of quantum pressure remaining after inflation ended, is directly linked to the bounce density, which in turn depends on the mass of the collapsing cloud that created our universe's black hole. All of these quantities are calculable. The predicted value for dark energy density is approximately 4 × 10⁻10 joules per meter. Current measurements show a value around 6 × 10⁻10, a remarkable match given the inherent uncertainties in both the theory and observations. In contrast, standard cosmology struggles to calculate dark energy, treating it as a free parameter, something that must be measured without any deeper understanding. The key difference is that bounce cosmology predicts dark energy rather than simply measuring it, eliminating the need for fine-tuning. It also explains inflation as a natural consequence of the bounce, rather than assuming the existence of a mysterious inflaton field. This makes bounce cosmology more predictive, more falsifiable, and more scientifically rigorous than the conventional approach. However, there is a crucial distinction. If dark energy stems from residual torsion, it should gradually decrease over time. As the universe expands, the quantum pressure that initially drove acceleration weakens. In the distant future, possibly trillions of years from now, dark energy may become negligible compared to other cosmic effects, testing the nature of dark energy. The predictions made by bounce cosmology differ significantly from those of standard cosmology, particularly regarding the behavior of dark energy. While standard cosmology asserts that dark energy remains constant, accelerating the universe indefinitely, the bounce theory suggests that dark energy will gradually weaken, causing acceleration to slow down over time. This distinction is testable. Current instruments cannot yet detect the gradual change in dark energy, but future observations spanning decades might reveal enough data to test these predictions. If dark energy proves to be truly constant, then bounce cosmology will need to be modified. However, if it decreases even slightly, standard cosmology will face serious challenges. Either way, the nature of dark energy is testable, and future experiments will provide definitive answers. This contrasts sharply with the anthropic explanation of dark energy, often invoked by standard cosmology, which suggests that we observe the particular value of dark energy simply because it is compatible with our existence. Bounce cosmology provides a deeper explanation for why the value of dark energy sits within a specific range, one that is conducive to the formation of galaxies and accelerating expansion. Too much dark energy would prevent galaxies from forming, while too little would prevent the expansion from accelerating. The value we observe is no coincidence, and bounce cosmology explains it naturally, eliminating the need for the anthropic principle. The predictive power of bounce cosmology. The dark energy value emerges directly from the physics of the bounce. Universes created by black hole bounces naturally have dark energy in the right range, not because of anthropic selection, but because of the dynamics at play during the collapse and bounce. The theory predicts this outcome without any fine-tuning. This straightforward explanation of dark energy resolves the cosmological constant problem and provides a simpler, more elegant solution to one of the greatest mysteries in physics. The bounce theory not only explains dark energy, but also unravels the true nature of cosmic inflation. Unlike the standard model, which requires an inflaton field with precisely the right energy density to drive inflation, bounce cosmology explains inflation as a natural consequence of the collapse and bounce process. The quantum pressure left behind after inflation provides the residual pressure that drives expansion, matching observed measurements of dark energy density with remarkable precision. This is what makes bounce cosmology not just a theory, but a scientifically testable framework. The theory doesn't rely on arbitrary parameters or luck. It uses known physics, Einstein's geometry combined with quantum mechanics, to predict and explain cosmic phenomena. And the theory's most profound implication is that we live inside a black hole that was formed from the collapse of matter in another universe. This seemingly bizarre conclusion is the logical consequence of the mathematics, and it has the potential to change everything we know about the cosmos. Spin and rotation inheritance. Black holes, unlike many might assume, are not always non-rotating. While not all black holes spin, any that form from collapsing matter with angular momentum inherit that rotation. This spin becomes embedded in the geometry of spacetime. In 1963, Roy Kerr's solution to Einstein's equations showed how rotating black holes warp spacetime more dramatically than non-rotating ones. A rotating black hole drags spacetime with it, creating a phenomenon called frame dragging. This effect has been confirmed through observation near event horizons. If our universe formed inside a rotating black hole, it would inherit that rotation. The angular momentum from the collapsing star would be embedded in the internal geometry of spacetime, manifesting as a cosmic spin axis. Nicodemus Poplavsky's calculations showed that when matter collapses into a spinning black hole and bounces, the resulting universe inherits a preferred axis of rotation. Spacetime itself rotates around this axis. This subtle rotation influences the formation of galaxies, causing them to spin up as they collapse under gravity, much like ice skaters pulling in their arms. Galaxies and rotation patterns. The direction of rotation in galaxies is not random. Galaxies formed in a universe created by a rotating black hole should statistically favor a preferred direction of rotation, aligned with the black hole's spin. While individual galaxies may rotate in different directions based on local conditions, the overall pattern should show a slight asymmetry. Around 2/3 of galaxies should rotate in one direction, with 1/3 rotating the other way. This prediction was confirmed by Leo Shamir's analysis of the James Webb Space Telescope data. He found that 2/3 of galaxies rotate in one direction, with 1/3 rotating in the opposite direction. This asymmetry, though subtle, is statistically significant, confirming the predictions made by the bounce theory. Moreover, galaxies farther from Earth show a stronger preferential rotation, consistent with the theory that the universe spun faster in its early stages. This discovery also ties into the phenomenon of cosmic parity violation. Some regions of the universe show a slight polarization asymmetry in the cosmic microwave background, with left-handed spirals outnumbering right-handed spirals. Standard cosmology cannot explain this, but bounce cosmology can. The inherited spin from the parent black hole imprints a preference for one-handedness in the child universe, which explains this otherwise mysterious observation. The birth of our universe. Our universe's peculiar characteristics, its rotation, its dark energy, and its overall structure, point to a common origin, a black hole in another universe. This black hole, formed by collapsing matter with angular momentum, spawned our cosmos. The spin of the collapsing matter became the rotation we observe in galaxies today, and the dynamics of the collapse and bounce process set the value of dark energy. This radical idea not only solves the mysteries of dark energy and inflation, but also suggests that our universe is one of many, each formed inside its own black hole, expanding and evolving within its own pocket of spacetime. The entire structure of the cosmos, the galaxies, the dark energy, the cosmic web, emerges naturally from the dynamics of gravitational collapse. We live inside a black hole, and that's the key to understanding everything about our universe. As the universe continues to expand, low-density regions form, eventually giving rise to new universes filled with galaxies like our own. Picture a stellar mass black hole roughly 10 times the mass of the Sun, created when a massive star exhausts its nuclear fuel and collapses. Its event horizon spans about 37 miles. From an external perspective, this region appears as a distorted patch of space where light orbits and matter spirals inward. Nothing escapes. It seems like a dead end. Inside the event horizon, however, something remarkable occurs. Matter falling inward does not collapse into a singularity. Instead, quantum pressure halts the collapse, causing space-time to rebound. Within a fraction of a second, as measured from inside the black hole, a new universe bursts into existence. This universe is small relative to our standards, with the black hole's mass setting its scale. A black hole with 10 stellar masses produces a universe containing roughly 3 × 10⁻32 kilograms of matter, with a Schwarzschild radius near 9 meters. Its average density is extraordinarily high. Structure forms quickly, stars ignite almost immediately, and galaxies cluster tightly. From inside, this universe has a short lifespan, yet from the outside, all events occur within finite time before the black hole evaporates via Hawking radiation. Once the black hole vanishes, so does the internal universe, unless it has spawned its own black holes, creating nested universes and continuing the cycle. Every black hole generates a universe. This is not speculation. It is a confirmed result of bounce cosmology. When collapse reaches maximum density, the quantum exclusion principle triggers a bounce, and the universe expands naturally. In 1992, Lee Mullen introduced the concept of cosmological natural selection. In this framework, universes reproduce through black holes. Each offspring universe inherits slightly altered physics due to quantum fluctuations during the bounce, modifying constants such as the strong nuclear force or electron mass. Universes producing more black holes generate more offspring, leading to cosmic evolution favoring black hole formation. Consequently, our universe may be fine-tuned to maximize black hole creation through this process. This framework elegantly explains why the physical constants in our universe take the values they do, without invoking fine-tuning or anthropic reasoning. Universes optimized for producing many stars and black holes dominate, and we exist within one of them. While we cannot observe other universes directly, the mechanism is testable. If every black hole contains a bouncing universe, quantum correlations might exist between our universe and its parent. These could appear as distinct patterns in the cosmic microwave background, temperature fluctuations, or polarization signals. Nicodemi's theory predicts torsion, a remnant effect from the bounce that may be detectable with sensitive instruments in the future. Bounce cosmology also predicts slight spatial curvature. A black hole's event horizon imposes boundary conditions, potentially producing detectable curvature. Current measurements have not ruled this out, but future satellites could test it. Positive curvature consistent with predictions would strongly support bounce cosmology, although it would not constitute absolute proof. The consequences are staggering. Every stellar mass black hole in our universe could contain its own universe. In the Milky Way, roughly 1% of 100 billion stars may become black holes, equating to around 1 billion universes. Across approximately 2 trillion galaxies in the observable universe, this leads to trillions of universes, each potentially spawning more, creating an infinite nested multiverse. We are not unique. Each universe evolves independently, experiencing its own expansion and structure formation, yet isolated from all others. This multiverse is a logical outcome of combining quantum mechanics and general relativity. If the governing equations are correct, infinite universes must exist. The mathematics demands it. In a much larger universe, the black hole harboring our cosmos may appear as an ordinary collapsed star. Inside, however, 13.8 billion years of cosmic history unfold. Galaxies form, stars ignite, and life and consciousness emerge, all invisible to observers outside. Lior Shamir identified an anomaly while analyzing galaxy rotations before the James Webb Telescope launched. He observed a directional preference. More galaxies rotated one way, especially near galactic poles. After thorough reanalysis, the asymmetry persisted, and distant galaxies exhibited a stronger bias, suggesting the early universe had a pronounced rotational axis. Shamir's studies, published from 2017 to 2020, concluded that the universe has a preferred axis of rotation. This aligns with the notion that our universe inherited rotation from a spinning black hole. The cosmic axis affects galactic orientation, and Nicodemi predicted in 2013 that universes born from rotating black holes would show directional asymmetry. Observations confirm this, and the effect diminishes over time as expansion dilutes angular momentum. Identifying the cosmic rotation axis allows estimation of the parent black hole's properties, its mass, spin, and formation time. Shamir estimated a mass of 5 times 10^52 solar masses and a spin near 80% of the maximum. While uncertain, these estimates offer insight into our cosmic origin. The universe might exhibit slight curvature. Planck data suggests near flatness within 1%, leaving room for subtle curvature. If future measurements, e.g. from the Euclid satellite, detect positive curvature near 2%, bounce cosmology gains strong support. Perfect flatness or negative curvature would challenge the theory. Bounce cosmology makes testable predictions. Positive curvature and directional galaxy rotation patterns. Future observations will confirm or refute these claims. If validated, it proves we live inside a black hole, that our universe resulted from a gravitational bounce, and that countless other universes exist within other black holes, evolving independently. The next decade may redefine cosmology entirely. The universe will eventually reveal whether it curves, and this curvature will determine if we are confined within a cosmic prison or drifting freely through unbounded space. In 1949, Kurt Gödel demonstrated a startling possibility. General relativity permits time travel to the past, not via wormholes or exotic matter, but simply by following paths through rotating spacetime known as closed time-like curves. These loops in reality could take you back to your own past. The mathematics are irrefutable. In a rotating universe, space-time twists and light cones tilt, merging past and future at the edges. Traveling far enough along a large enough circle could bring you before your departure. The distinction between past and future becomes observer-dependent, straddling the boundary between physics and philosophy. Thankfully, our universe rotates too slowly for closed time-like curves to form. Observations indicate a rotation rate effectively zero, less than 1/10 quadrillionth of a degree per century, far too slow to produce time loops or paradoxes. We are safe from causal chaos. Yet, the early universe was different. Near the bounce, its rotation was intense, with angular momentum concentrated in a smaller volume, producing much higher rotation rates. As expansion proceeded, rotation slowed gradually. However, shortly after the bounce, rotation could have been sufficient to generate closed time-like curves. This implies a bizarre possibility. During the first microseconds post-bounce, causality might have been ambiguous. Events could influence their own past. Quantum fluctuations might have looped backward. Early conditions may have been partially shaped by future events, forming loops in cosmic causality. We cannot observe this directly because the universe was opaque to light until 380,000 years post-bounce. Everything earlier is hidden behind the cosmic microwave background. Quantum entanglement could preserve traces of this causal looping. If closed time-like curves existed, they would produce distinct entanglement patterns, correlations between regions otherwise causally disconnected. Such patterns may appear as anomalies in the cosmic microwave background, including unusual temperature correlations or alignments in the quadrupole and octupole. Some researchers propose these anomalies reflect early universe time loops. Interpretations remain debated. Roger Penrose suggests these correlations are real and could signal echoes from a previous universe that collapsed and bounced. If true, the microwave background may carry information from the prior cycle. Though statistical strength is weak, future high-precision observations might confirm or refute this. The consequences are profound. If causality was uncertain during the bounce, cosmic determinism would fail. The universe's initial conditions would be influenced not only by past states, but also by future states, self-causation. The universe could have partially created itself through temporal loops. While it sounds like science fiction, the mathematics supports it. General relativity allows it, and quantum mechanics may even require it. Physics can be stranger than fiction, which must remain plausible. Mathematics further indicates that if our universe inherited rotation from a spinning black hole, this rotation would have peaked in the earliest moments, warping time, forming loops and briefly muddling causality. We live in the aftermath, where causality flows normally. Yet our origin may be non-linear, with initial conditions bootstrapping existence through quantum temporal loops. This implies that what came before the Big Bang has no answer. There is no linear cause and effect, only a closed loop where past and future merge. Time travel is impossible now, but may have been feasible during the bounce. Every solution to Einstein's equations allows time reversal. Running the equations backward transforms black holes collapsing into singularities into white holes, which explode outward. A black hole's event horizon, which traps light, reverses in a white hole, where nothing enters, but everything exits. The math is symmetric. Both black and white holes are permitted. White holes are bizarre. Matter and light burst outward, and nothing enters. They are the opposite of black holes. No white hole has been observed, and most physicists believe they do not exist, not because forbidden mathematically, but because their formation seems impossible. A white hole requires sudden matter creation, violating energy conservation. However, our universe resembles a white hole. Expansion from a dense state, with all matter moving outward, mirrors white hole behavior. The Big Bang itself is a white hole event, the bounce and the start of expansion. The connection between black and white holes is not coincidental. Inside a black hole beyond its event horizon, the geometry mirrors a white hole interior. Perspective differs. Falling into a black hole, one sees expansion internally. The singularity lies in the future, and time flows inward. An external observer sees collapse. Both views are valid in their frames. Relativity depends on observer motion and location. No absolute perspective exists. We perceive expansion from within. The singularity lies in our past, but never truly existed, prevented by the bounce. We see the white hole interior, while from the parent universe, it appears as a black hole. Classical collapse occurred, forming a new event horizon. White holes exist, and we reside inside one. Universes formed from black hole bounces occupy white hole interiors. Their seemingly impossible conditions arise naturally. Matter explodes outward as the collapse reverses, conserving energy. White holes are not eternal. From the parent universe's perspective, black holes evaporate via Hawking radiation. When the last quantum escapes, the white hole interior vanishes, erasing billions of years of internal history. If our universe formed black holes, those contain their own white hole interiors and child universes. As black holes evaporate, these child universes persist, isolated yet real, continuing an infinite chain of nested realities, created, never destroyed, merely disconnected. White hole geometry explains why escape is impossible. The cosmological horizon acts like a white hole horizon. We can move outward, but no information crosses the horizon. It is a geometric constraint, not a physical barrier. Accelerate toward the horizon at light speed, and it recedes equally, preventing escape. Galaxies near the horizon recede at nearly light speed. More distant galaxies move faster than light. This recession is space expansion, not motion. From the parent universe, nothing unusual occurs. Our black hole appears stable, with matter fallen billions of years ago. Hawking radiation leaks slowly. Evaporation takes unimaginable time, up to 10⁻100 years for a black hole our size. Thus, we exist in a strange state, inside a white hole, expanding toward infinity, surrounded by a horizon that blocks escape. External observers see a black hole gradually evaporating, yet two realities coexist, both true, separated by the event horizon. The James Webb Space Telescope recently uncovered an astonishing phenomenon: galaxies that, according to current scientific understanding, should not exist. These galaxies are not merely unusual. They appear impossible within the framework of standard cosmological models. They are so massive and evolved that their formation seems to demand more time than the universe's current estimated age. The first of these, named Glass Z13, was detected in 2022 at a redshift of 13, with light traveling 13.4 billion years to reach Earth. This galaxy formed when the universe was just 300 million years old, already containing billions of stars and showing substantial structure. Conventional theory predicts a gradual process. Small clumps of dark matter collapse, gas accumulates, stars ignite, and galaxies merge over billions of years. At 300 million years, galaxies should be small, primitive, mostly gaseous, with few stars and minimal structure. Yet Webb observed galaxies far more massive and evolved than anticipated. The anomalies continued. Another galaxy, Jade's GS-Z140, was discovered at a redshift of 14.2, with light traveling 13.6 billion years. It formed only 250 million years after the Big Bang and was even more developed than Glass Z13. These observations challenge the established models of structure formation, which cannot proceed this quickly under known physics. Some researchers proposed modifications to existing models, such as faster dark matter clustering, enhanced gas cooling, or more efficient early star formation. However, these adjustments often appear forced and lack robust theoretical support. Consequently, some scientists began questioning the model itself. Leo Shamir suggested that distance measurements might be skewed by cosmic rotation effects. If these galaxies are closer than calculated, they would have more time to form, resolving the paradox without altering fundamental cosmological theories. An alternative explanation comes from bounce cosmology, which proposes that the universe could be far older than the standard 13.8 billion years, perhaps closer to 25 billion years, if the cosmic bounce occurred earlier. However, this idea conflicts with radioactive dating, anchored by Earth's oldest rocks, which implies a younger universe. Reconciling this would require considering the effects of time dilation in a rotating universe. General relativity allows time to flow differently depending on gravitational fields or rotational reference frames, meaning cosmic rotation could make the universe appear younger than it truly is. Though speculative, this could explain some observational discrepancies. As additional high redshift galaxies are discovered, the tension between observation and theory increases. Either our understanding of galaxy formation is incomplete, or significant errors exist in cosmic distance measurements. If the latter, the entire cosmic map may need recalibration, fundamentally reshaping our perception of the universe. Raj Pathria's 1972 proposal suggested that the universe might share properties with black holes, but it was largely ignored despite sound mathematics and testable predictions. Interest resurfaced in the 1990s with Lee Smolin's cosmological natural selection, proposing that universes evolve through black hole formation. Yet, mainstream science remained skeptical. By the 2010s, research including Nicodemi's work indicated that black holes could generate expanding universes via a bounce, avoiding singularities. Observational support emerged from galaxy rotation asymmetries and the early massive galaxies observed by Webb. Despite resistance from scientists invested in the Big Bang paradigm, alternative theories like bounce cosmology are gaining traction. Enrique Gastiaga demonstrated that bounces are not only plausible, but inevitable, producing universes through black holes. The theory provides testable predictions, including positive curvature and distinct rotational patterns. Future observations could compel the scientific community to reconsider these models. Confirming an older universe or earlier galaxy formation would trigger a paradigm shift. The upcoming European Space Agency Arrakis mission, launching in 2030, aims to measure the universe's curvature with unprecedented precision, potentially confirming predictions of bounce cosmology. Ultimately, we may soon obtain conclusive answers, either reinforcing the standard model or unveiling a radically new understanding of the cosmos. If bounce cosmology is validated, it would revolutionize cosmology, transforming our comprehension of space, time, and the very essence of existence. If negative curvature is observed, both current cosmological models would fail, suggesting an entirely new framework for understanding the universe. Negative curvature implies an open, hyperbolic cosmos, fundamentally different from present theories, requiring new physics and explanations. Most cosmologists currently predict near flatness, with deviations smaller than 0.1%. Standard inflationary models forecast a flat universe, and as observations improve, measurements continue to trend towards zero curvature. Yet, nature often surprises. Unexpected results demand adaptation of theories. Scientific progress thrives on such challenges. In this context, DocuVerse could play a pivotal role. The detection of slight positive curvature would astonish scientists and lend credibility to black hole cosmology. Such a finding would vindicate decades of work by Pathria, Poplawski, Gastiaga, and others, while challenging the prevailing assumption of perfect flatness inherent in standard inflation. Whether confirming the standard model or reshaping our cosmic understanding, the uncertainty will soon be resolved. Within the coming years, we will finally know whether our universe resides inside a black hole. Direct observational data will convert speculation into empirical knowledge. The mission to test these predictions is already in progress. Engineers are refining instruments, technicians assembling components, and the launch vehicle is being prepared, all targeting a 2030 deployment. Assuming no delays, the satellite will reach orbit as scheduled, and within 6 years, data will begin arriving. By 2037, definitive conclusions regarding the universe's curvature will emerge. If positive curvature is confirmed, our perception of reality could undergo a dramatic transformation. The frameworks of cosmology might be rewritten, and educational materials would require substantial updates. Understanding that we inhabit a black hole would carry profound philosophical and scientific significance. Now, picture yourself observing from the parent universe. A black hole appears as an ordinary collapsed star, nothing unusual. Its mass is measured, Hawking radiation monitored, and typical black hole features analyzed. Yet inside, an entire universe exists, trillions of galaxies, innumerable stars, countless planets, and potentially life and consciousness, all hidden behind the event horizon. Externally, the black hole seems ordinary, but internally it hosts an immense, expanding universe teeming with possibilities. This is precisely the scenario we inhabit. Though this knowledge does not affect day-to-day life, stars burn, planets orbit, and life continues, the philosophical implications are vast. We are not simply in the universe, we reside within a universe. Each universe exists inside its own black hole, isolated from the vastness beyond. The parent universe could be unimaginably immense, potentially infinite. What seems vast from our perspective is minuscule from the parent universe's vantage. This may unsettle some, as it removes the necessity of a singular origin or first cause. Yet for others, it is liberating. Existence simply is, with universes cycling endlessly within black holes. Physically, whether we inhabit a black hole does not alter our immediate experience. We continue probing, observing, and testing cosmic theories. However, if our universe truly resides within a black hole, the implications multiply. Other universes could exist beyond reach, each developing its own civilizations and knowledge systems, forever inaccessible to us. The event horizon constitutes an absolute barrier, preventing interaction between universes. Philosophically, this reframes cosmic significance. We would be one of countless universes, each isolated within its own black hole. While our universe is understood in detail, what lies beyond remains inaccessible. If bounce cosmology proves incorrect and our universe is not inside a black hole, we might then occupy the center of a singular, unique universe, a position of unparalleled cosmic significance. This scenario leads naturally to the concept of the eternal cycle. Our universe originated from matter, collapsing inside a black hole within a parent universe, which itself emerged from a grandparent universe, continuing ad infinitum. This chain of black holes giving birth to universes is perpetual. Whether our universe will collapse or expand indefinitely remains unknown. Some theorists suggest eventual contraction, leading to new bounces, each cycle slightly different from the last, exploring endless variations. If dark energy diminishes, gravity could reverse expansion, initiating a new bounce. In this framework, the universe would undergo infinite cycles of expansion, contraction, and rebirth. Over countless iterations, universes evolve naturally towards stable configurations, optimizing through a cosmic trial and error process. This cyclical dynamic addresses the fine-tuning problem. Unstable universes collapse quickly, while stable universes endure. Current observations indicate expansion driven by dark energy. Some theorists propose that this energy may eventually wane, producing a reversal of expansion. If correct, a perpetual cycle of cosmic collapse and reformation would ensue, each iteration exploring new possibilities. An alternative framework is Penrose's Conformal Cyclic Cosmology, in which the universe ends in heat death and a new Big Bang occurs. Unlike bounce cosmology, this model does not involve black holes or parent universes. Both theories, however, imply that time may not be fundamental, but part of a broader overarching structure. The ultimate revelation of cosmology may be that the universe is eternal and cyclic, with time emerging as an aspect of experience rather than a primary property. As our comprehension of the cosmos deepens, we may realize that our universe is one of many, part of an infinite sequence of cycles, each evolving under unique conditions. This perspective transforms our view of reality, from linear and finite to a continuous, eternal progression of cosmic evolution.